This video shows the block commutation of a brushless DC motor, also called EC motor, with ironless winding. Based on an animation, it shows the schematic design of an EC motor and explains how the torque is generated, or in short, what needs to happen so that the motor will operate. First, we have a look at the design. On the right is the cross-section of a maxon EC motor. In the center is the rotor with its two-pole permanent magnet mounted on the shaft, shown in gray. The permanent magnet is diametrically magnetized. On the left, the magnetic north pole in red, on the right, the south pole in green. This results in magnetic field lines which are guided through the laminated magnetic return. For simplicity, we replace the magnetic flux with a symbolic arrow. The three-phase winding is in the stator of the brushless DC motor. The three digital Hall sensors, here in blue, are mounted at an angle of 120 degrees. To simplify, we assume that the Hall sensors directly monitoring the power magnet. The Hall sensors detect the position of the rotor. The feedback signal of the Hall sensor is typically 5 volt at the north pole and 0 volt at the south pole. The brushless design allows a longer service life and higher speeds to be achieved. Since commutation with brushes, as in a DC motor, is not possible, commutation electronics are always required. This electronic device is connected directly to the windings and the Hall sensors. The commutation electronics are supplied with a DC supply voltage. In our animation, it is symbolized with a small plus and minus sign. The power stage of the electronics consists of 6 MOSFETs. 3 of them are used to connect the motor lines to the positive supply voltage. The lower 3 MOSFETs connect the lines to the negative voltage or ground. The commutation logic switches the individual MOSFETs in the power output stage. The logic reads in the Hall sensor signals and supplies the 3 motor phases with the positive or negative voltage accordingly. In this starting position, the Hall sensors generate the following signals. The lower left Hall sensor provides a high level, due to the near north pole. The lower right Hall sensor provides a low level, due to the near south pole. The upper Hall sensor is just switching to a high state. The commutation logic knows that with this signal combination and the clockwise rotation of the motor, the current must flow from phase 1 to phase 2 and powers the respective 2 MOSFETs. The now current-carrying winding generates a magnetic field from bottom left to top right. The permanent magnet begins to align and the rotor rotates. After a rotation angle of 60 degrees, the Hall sensors on the left start seeing the south pole and its output switches to the low level. The commutation logic now switches the positive pole of the DC power supply from phase 1 to 3. The magnetic field of the winding advances by 60 degrees and the rotor continues to rotate. After the rotor has turned 60 degrees, the Hall sensor on the right switches to the high level and the pattern of the Hall sensors changes again. The commutation logic switches the negative pole of the DC voltage source from phase 2 to 1. Again, the field of the winding advances by 60 degrees, and the rotor continues to rotate. This process is repeated every 60 degrees. After 6 commutation intervals, the rotor has completed 1 full revolution and is back at its starting position. In reality, of course, the motor rotates continuously. Now you know how the block commutation of a brush DC motor works. On our website, maxongroup.com, you can find more information and videos, such as the commutation of a multipole brushless motor. Thank you and goodbye.